Ready? All right. This is made for like a 5'8" person, which I am not. So I'm going to assume that you guys are you mean to be here since it's early and everyone's probably dealing with the after effects of last night, right? So this is the talk on credit card tokenization and some of the cool hacks and mistakes and fun things we can do with it. But first, since I've actually never been live streamed on the internet before and my poor wife and kids are actually stuck in a hotel room, I'm going to say hi to them real quick, and then you can go back to Saturday morning cartoons now, because it'll be boring for you, right? So anyway, my name's Tim. Unlike hacker Jack Sparrow, I am actually less famous than him, so you probably have heard of him and not me. That's fine. I've got 15 years of experience in IT doing defender, builder, breaker roles. Currently, I'm the director of the red team at Walmart Labs, which is Fortune 1, the largest company in the world. We have obviously a really cool big network, millions of IPs in 28 countries. We're the second largest e-commerce in the United States. We've got millions of customers in our stores and in our web properties every single week, which is a very, very fun thing. It makes this kind of work and security work much more enjoyable and valuable, right? If you're into credentials, alphabet soup, CVs, you want to see my credit score, LinkedIn probably has it. Connect with me there. Let's get a couple disclaimers out of the way real fast. So number one, there's a couple things. We have 277 slides in 45 minutes. So this is going to be like a Saturday morning ADHD cartoon for you, okay? We're going to keep you awake, I promise. I love this scene from Willy Wonka, accident indemnity clause, not among friends. So first disclaimer, this presentation is my work, right? It's not my opinion, or it's my opinion, it's not my employer's opinion in any way. All the examples that you see today are going to be from actual, real e-commerce applications from a variety of places. They're all sanitized. I won't tell you where they're from. They should all be fixed now anyway, all the ones that I had anything to do with. I've never been a PCI QSA, so if you came here to figure out how to get certified, you came to the wrong spot, and I can't help you with that. So take any advice at your own risk, don't run with scissors, and let's call that horse dead, okay? So today we're going to be talking about a lot of stuff, all these different attacks. You see there's 6 different kinds of issues we're going to be dealing with, but first we're going to start with some background info so that we're all on the same page with terminology, right? So let's, real quick, just so I can kind of tailor this a little bit to you guys. How many of you guys are defenders, your corporate defender roles of some sort? Okay, good. How many of you guys are builders? You build systems, you're software developers? Okay. How many of you guys are breakers, pen testers, red team? Okay, this is a good mix. Every other presentation I've done, it's been very much biased to the first 2 groups. It's good to see a nice even distribution there. So how many of you guys use credit card tokenization at work? Okay, and then how many of you aren't even sure if you do or not? You maybe take credit cards and who knows, right? Okay, usually that category is actually the biggest, most number of hands that goes up. I'm like, I don't know, right? So, some background info. So there's these 2 concepts we're going to deal with a lot, truncation and tokenization. So let's define truncation first, right? So we have a credit card number, it's got the 16 digits, and basically truncation is taking the 6 digits in the middle, kind of blacking them out, right? And that's okay. And what's interesting about this, if you dig into it, the credit card number is actually, it's a formula, right? There are an issuer, a bank ID, an account number, and a check digit in there. So the first time I heard about truncation, the first thing that came to my head is, how hard is it to guess the missing digits? And I'm sorry if you want to grab a screenshot or a picture of my slides. My slides are going to go so fast, you're going to get the next one probably by the time your phone flashes. I'll post all these slides when we're done. So, how hard is it to guess the missing digits, right? So it's, there's 10 choices, 6 characters, right? 10 to the 6th power, that's a million, right? So it's worst case, a million guesses, right? So on the average case, we know that that's 500,000, right? But there's this really cool thing called the Loon algorithm, or the Mod 10 rule, if you're familiar with it. Credit cards have to comply with it, which basically means that last digit's a check digit, like we talked about, right? So that check digit actually makes it 10 to the 5th power, or 100,000 guesses in the worst case, or 50,000 on average. That's still a lot, but it's very easy to brute force. Python code, you can get 5, 7, 10 seconds of code execution time, you can generate all those in the middle. And yet, it's really funny to me because PCI allows truncated storage of credit card numbers. And I always like, okay, scratch my head, why? But they've got this nice little warning in section 3.4. If you're into that, go check it out. This is not a PCI certification talk, so this is as close to compliancy type stuff I will say today. So homework for later if you're into that kind of thing. So first off, what is tokenization? We know what truncation is. Tokenization is really the simple concept that I'm going to take an actual credit card number that's valuable and I'm going to replace it with something that's not valuable, right? A non-sensitive tokenization, or non-sensitive token. So we got.
Hi folks, I'm Geek here. Unfortunately, another video problem, so come back at about the 8-minute, 6-second mark when you want to listen to audio. In the meantime, here's what we have so far with the video. Sorry for the inconvenience.
Developer, and in that scenario, that person would have access to your commerce apps database, and then all the data that's in it, like the customer billing info, the truncated credit cards, the tokens, and then they'd have some knowledge of how the actual tokenization architecture works as well. So we're talking URLs, web service APIs, access to the request logs potentially, and so that's what I define as this partial access to a credit card. But it turns out, there's more to it than that. By the way, I've never seen the movie Shopaholic, but I think this 30-second thing that you see on the trailer that gives away probably the entire movie is hilarious. So we're going to refer to this a couple times. She pulls the credit card out of the block device, right? So anyway, so thanks to doing red teaming in my current role, it's actually changed my mindset. I realized I had some bias on this, right? So it turns out that an attacker during a breach scenario may very well have this partial access, right? So whereas I couched this before as a malicious insider that decides he wants to game the system internally to do harm, this could very well be somebody that's doing something like this, just especially when we have a PCI focus, because where's all of our time and attention and our money, right? It's in that nice little red square. And then where in the world do the red teams and do the breach actual adversaries like to go? They like to go to that blue square, right? So the credit cards are in red, and that partial access that we're talking about is in this blue area where your controls aren't as strong, right? Where you're probably not looking as closely, right? So this really well could be a malicious insider, but it's just as likely that it could be a an actual adversary like in the final stages of a breach, right? So let's talk about the best case scenario, right? The best case scenario in this partial access is the attacker has to enumerate credit cards on that same level of truncation, right? Which we just talked about a minute ago. That was 50,000 guesses on average, right? Per card. So that's a whole lot of this, right? A lot of hammering, a lot of brute, a lot of noise. It's not great. It's not ideal for an attacker, especially considering that we're talking about online validation, right? So in that best case scenario, if I'm going to generate a token, I'm actually going to have to run a transaction. And this is really common with web apps, right? And if you do it right, for me to give you a credit card, I'm going to probably have to go end to end all the way to a bank and back. And so that when that happens, those live transactions against that credit card auth service, we now have fraud detection, and we have throttling, and we have all these things that come in there and basically save the day, right? So at that point, we're caught, right? So, caught. So let's talk about the worst case. And the worst case scenario, and this is actually probably true in both cases, that the tokenization URL is internet facing. And the reason why it's important to note this, it has to be internet facing, right? Because we're talking about this scenario, right? The customer down here in the bottom has to be able to talk up there to the payment server in that red square. Because if they give the credit card to the blue square, that means the blue square, right, suddenly has PCI cooties, right? Because they touched that credit card. So again, this theme, we're going to see these dumb cooties from Milton Bradley or whoever it was a dozen times a day, so don't throw tomatoes yet. So anyway, so the Commerce app in this worst case scenario is going to perform authentication and authorization. We know that. We figured all that out. Top 10 OAuth, got it, right? But the payment service actually doesn't in our worst case scenario. And believe it or not, this is typical. Let me explain. You gotta ask yourself why. Why, what do you mean? You know, we have authentication on our app. You have to log in. You have to create a shopping cart. You have an account. We do all that stuff. We validate your email address is real. But it goes back to this whole logical separation, right? So the payment server is logically separated in a different PCI DMZ, right? So here again, we got this user, he's got store.example.com and he's got payment.example.com. They're separate, right? They're probably in different DMZs. There's no sharing of session state data because it, you know, again, going back to the PCI cooties thing. So we have different DNS domains, you notice, and so what happens with different DNS domains? Well, you have to go out of your way to make sure cookies go over there, right? Because cookies will probably be set specifically at the host name, and if you set to the parent, right, so just example.com in this scenario, then you're going to start exchanging data, but you can't actually validate that session because if you do, you got PCI cooties again, right? So here's this notion that you have to have this logical separation. We've got these three parties, and they can only talk with certain really well-defined rules. Another really common thing is that, and especially important for our worst case scenario, is that there's no request throttling or very, very little request throttling on the payment service. And believe it or not, this is actually typical as well, because when we spin these services up, we don't teach these developers to think this way, and it's really, really hard to identify abusers, right? We'll talk about that a little bit. So kind of think of this as like this design flaw 0 day, right? So let's get into an example. This is based on a real live web application that existed at one time. So step one, we got a customer checking out. They got a shopping cart. They're on store.example.com. Then it comes time to actually place that payment request. They're going to send that payment request on over to payment.example.com, right? And when this happens, there's a couple ways this typically goes down. You probably have experienced both of you. In fact, whether you're paying attention or not, I'm sure you probably checked out somewhere that does one or both of these two scenarios. You either get a brand new user interface that's hosted on a third-party domain or a different domain. You get redirected. Your browser's over here now. Make your payment. And you see this a lot on low-scale, smaller mom-and-pop online retailers because they don't want to host that content. And then on the big-scale sites that where brand and maintaining the same look and feel is important, you'll have some JavaScript magic that happens in the browser that grabs that token and sends it on over. And so you get a web request that looks something like this, right? We're going to post out to the Generate Credit Card Token API. You have host, there is the payment.example.com, so you see it's going to the payment server, it's not going to the app server. There's some session cookies that were there. We snipped them out for the example. There's a credit card number and expiration date. Great. So what do we do? As attackers, the very first thing we do when we see something like this is let's send that same request again. This time, let's strip out the cookies. And if there's any auth headers or any other material, any other unnecessary headers, let's pare that down to the bare minimum and let's just see what happens. And believe it or not, what actually happens is more often than not, your server will just give you 200, okay, here's your token, right? Your JSON payload, there's your token. There's no access denied response. So I remember the first time going through that going, that's stupid, right? Why did that happen? So even though there's no cookies in there, the server, I give it a PAN. When I say PAN, that's PCI speak for primary account number. I gave you a 16-digit number, and I get a tip token back, no cookies required. So let's talk about why. So back to this whole different servers, different domain thing, right? So we've got these two places. There's no sharing of data because, again, PCI cooties, again, theme. We're going to get this in your head. You're going to like have this, ingrained in your vision before we're done. So attackers with this partial access. So here's the scenario how we can actually beat this, right? What we're going to do is we're going to compute all the possible PANs, And then what we're going to do, based on the truncated credit card numbers that we've found someplace, right? So we're the insider, or we're the guy in the breach, the final stages of breach. We've got access to these truncated primary account numbers, right? So we're going to go compute all of them. And then, that's obviously going to be about 50,000 in the average case, right? So once we iterate through each one of them, we're basically just going to submit each one anonymously, because even if we didn't, even if it required cookies or whatever, we could just strip those out. But we're just going to hammer that tokenization API. You get bonus points, by the way, if at this stage you decide you're going to just randomize this, or you're going to take this load and split it among a botnet or just a bunch of cloud hosts or whatever. You just find some way to distribute that load for threading and for obfuscation purposes, right, for what you're trying to do. And then basically all you're going to do is you're going to just sit here and you're going to look for responses back. And when you get a response back that matches that token that went with that truncated PAN, that truncated credit card number that was in that commerce app, then you win, right? So we finally have this. Boom, got the credit card out. So throttling on the payment server is difficult. Let's talk about why. Well, for one, we've hammered in this, right? Like, there's no unique cookies here. And even if there were, the attacker could throw them away. So we could try blocking by IP address, but 1999 called and said, what about added customers, right? That's a really bad idea. And what if your adversary's smart and just says, I'm just going to hide through a bunch of IPs, right? It's really, really hard to do it. And just think, like, this is the scenario of Bitcoin mining, right? We're going to just distribute this load out and let them all just kind of make requests randomly. And we just need to slow cook the payment server, and we can get past this scenario. So how do we solve this? So what we really need to do is we need to talk about authentication handoffs across domain boundaries, or as we said back in 2004 or 2003, federated authentication, right? This is not really a new idea, but for some reason, we don't see this. No one thinks to apply this to payment systems, right? So here's kind of what we're looking at. Same kind of example before, but let's just suppose this time we have a little auth token that went with it. And keep in mind the auth token needs to be generated by the Commerce app server. And also, don't implement it in JavaScript. Why? Because obviously attackers can just unravel that logic, whatever it is that generates that token, and then we're back to the same scenario, so you might as well not even do that. For some reason, we still have to tell developers, don't do it in JavaScript. So note for everyone, don't do it in JavaScript. Right? So, and this is similar to, in the early days of tokenization, you'd see some of the commercial payment gateways would actually do things like this, where they would do what they'd use signed HMACs, right? And they would sign the data elements, right? So that's the solution to that. It's really, really not a hard solution, and really not a really hard problem at the end of the day, but for some reason, it's still kind of a prevalent problem. So let's look at the second set of attacks, and these are side channels, right? Side channels are some of my favorite variety of attacks because they're pretty clever, right? If you're not familiar with what side channels are, it's basically an unintended channel of information flow. So our goal with the side channel attack is to find basically a 1 or a 0 in the noise, right? So for those of you with a Comp E or an EE background, we're talking about Shannon's law. And for those of you that don't know who Shannon is, if you're really bored and need some extra credit homework or whatever, there you go. Go dig that up. Wikipedia's got a decent article. So we're talking about that, right? So the first step, we're going to do some timing attacks. It's not some hammer time, but this again, I know that this is the 9 a.m. slot and I need to wake you guys up. So timing attacks turn out to be very, very difficult to prevent, right? So because we don't teach developers to think about them. So for the inspiration for this particular attack, we want to draw back on this last example, right, where we have partial access to truncated PANs. And we also want to think about maybe in a scenario where we have like an account takeover where an attacker can view an online customer's account and kind of view their saved credit cards, right? And so the trick we're going to do here is we're basically going to create a batch of primary account numbers. We're just going to generate random ones, right? We're going to submit them all to the server, and then we're going to record, put a stopwatch on it, meter it. How long did it take? And then we're going to take that same exact batch, and we're going to throw it straight back through a second time and measure it a second time. And then what happens? We've got some kind of predictable delta in the response times. So it looks something like this. We got this nice table here. It's probably hard to see, but basically we got a bunch of credit card numbers that we've thrown through there. We have response times all the way through. We got miss, because they're all hanging around 280 milliseconds or so. And then eventually we get one that's down around 120 milliseconds or whatever, and that's like, E12, C4, whatever. Okay, you sunk my battleship, right? This is basically what we're doing is we're playing battleship with the tokenization server. So in that particular scenario, a previously tokenized PAN, so in other words, a credit card that the payment server has seen before, took about half as long. And this varies. It's based on the actual implementation. I've seen scenarios where it's the reverse, right? Where a token that's been, a credit card that's been seen by the tokenization server actually takes longer. So the point is we need to find that delta. We need to find that signal. It doesn't matter which direction. So in this particular example, I have some mocked up little pseudocode here. Take a look at that for a second. Does anyone see the flaw? Did you catch it? I know I throw it through code at you really fast at like 9:15 in the morning. Yeah, whatever. So new tokens actually hit the database twice. Let's go back and look at that one more time. Right? So this particular case, we're doing a SHA-256 hash. Pay no attention to the fact, just assume that that little pseudocode is actually salting that hash, right? We're doing something to generate some kind of a token. And basically we're going and saying, hey, database, have you seen this token before? And if the results are yeah, I've got one, I got a hit. Basically, I'm just going to return that. So I hit the database once, if I've seen it before, and I'm out. If it's one that I've never seen before, I'm going to generate that token, and I'm going to go and insert it in the credit card table, right? So what happened? I hit the database a second time, right? So those two sets of I/O is much, much slower than computations in memory, right? So in that particular case, if we got a response time roughly about 100 milliseconds, we knew we got the actual credit card. So just something to keep in mind. By the way, the solution to this, does anyone have an idea on how the best way to solve this? This is really hard. Yeah, that's one thing I like to say to people. I like to say to developers, hit the database a second time. Some DBAs are not a fan of that, right, because there's locks. I don't know of a better way to do it. So some people like to go and insert random sleeps. Yeah, exactly. So you could insert a random sleep in here. And my previous iteration of my slide deck actually had this covered, and for some reason I omitted this part, so I'm freewheeling it here. But so basically what you could do is you could sleep a random amount of time, but the problem with that is if you have peak business times a year, let's say you're really busy during the Christmas holiday, and maybe your average response times increase by 100 to 200, 300 milliseconds just because of the load that's in your environment. If you slept for a hard-coded 50 or 150 milliseconds or whatever that is, then you're still going to have that tell, right? So that's why I'm a big fan of going and hitting the database a second time. But you need to make sure that your DBAs don't have some really cool caching stuff going on there where it says, we've already done that query before, here's your result set, and give you a real fast response, because otherwise you'll have the same problem. So it's hard, right? It's a really, really hard problem to solve. So the second side channel we're going to talk about is, I like to call these my profile attacks, right? So this is the idea that an attacker basically gets a customer session cookies or credentials. We commonly refer to this as account takeover scenarios, right? So the Yahoo data dump that just happened, or Yahoo breach that just happened, we'll probably get a data dump from that, and there'll be creds out there, and people will try to see if those creds were used. That's a real common way to do account takeovers, right? That's another talk entirely. But if that happens, an attacker gets in there, basically what the attacker wants to do is go to the My Profile page and say, what truncated credit card numbers, what truncated PANs are there in the saved credit card page or the list, right? And so at this point, when we bring this up, my experience with developers has been, but our commerce app doesn't even have credit card data in it. We just have tokens, right? So the app lives in that nice little blue square, and the credit cards live in red, to which I say, okay. But this is actually a real problem, right? This still affects a lot of apps today. I won't name any, but there are apps that you can actually go out that you probably shop at, you probably have profiles built on right now that you can actually go do this to. So the idea is basically, hey, same idea, I'm gonna go submit a possible PAN. I've got that truncated number, right? I'm gonna guess what the rest of the digits are. I'm gonna submit it. Make sure you use the same billing information that's on the profile, because this is a lot of times how they tie in the uniqueness, right? If you put in some different street address, right, it's probably going to view that as a different payment method. But if you submit it in, basically we're going to try to get a collision here, right? So, and then when we're done, after we submit it, we want to see, basically count, how many saved payment profiles are there now, right? So if the count of saved payment methods on the profile went up by 1, that means we missed, right? Back to the whole E12 miss. You didn't sync my battleship concept, right? So if you're automating this, bonus points for going in there and deleting that previous one. So if there was 3, you take over an account, and you submit a PAN that matches one of them, and it turns out now you got 4, make sure your script is smart enough to go back there, delete that 4th one you just submitted, and just keep going through this thing until eventually you submit a request and you had 3 before and you have 3 after, right? So if the count is the same, we're back to this. You sunk my battleship. And again, all we're doing here is we're forcing the server to provide a Boolean logic response, right? So another note on this, right? So a lot of places that give you the card type won't give you an actual truncated card number in the sense of that they just block out the middle 6. A lot of times they'll give you the last 4 digits, the expiration month and year, and they'll give you the card type. So they'll say it's a Visa. Okay. Just means it's more than 50,000 guesses, right? Because, obviously I don't have all those digits in the beginning, but if I know it's a Visa and I know it's the United States, I already know a good deal of information about those first 4 to 6 digits, right? So I can kind of figure that out based on rules that the industry follows, the banking industry follows, right? So it's still possible. And so actually this is where we need Jim Carrey going. They're telling me there's a chance, right? So how do we solve this, right? Basically, the solution that we always recommend is always add a new payment method, right? It doesn't matter that the billing address matches or even that the primary account number, the actual credit card number matches some previous thing in here. Just go ahead and add another one, right? And this logic usually lives on the tokenization server, right? Because again, going back to the whole PCI cooties thing, the app server is not going to actually see that credit card number, so we're sending this off over there. So the people that handle the actual payment, they're the ones that need to actually generate this, right? And you're going to have this uphill battle with them. Tell them, give them a nice hug and say, it's okay. We don't have to be efficient with our token records, right? It's okay to add yet another line to the database, right? Because when we add another row, that just means we're not getting rid of we're not divulging our customers' credit cards, right? So next side channel, helpful headers. If you have a RESTful service geek in your organization, you'll relate to this. Does anyone have a RESTful service geek? You guys know one? Do I have any that were willing to admit that they are one? You'll see. Okay, so RESTful service geeks love their status codes. Those people that will argue with you about, well, that's not technically RESTful because you always return 200 okay. Or that's not really RESTful because you do some weird little nuance thing. It doesn't matter that you got JSON and that you're using HTTP verbs, but maybe you're not using all of the verbs. Stuff like that. These are the guys I'm talking about, right? So they love their status codes. They love things like this, and obviously this is not an exhaustive list. There are way more status codes than I normally ever see, that you guys probably ever see. But the ones that are up here are interesting, right? So what if you have an API to generate a credit card token and you get a request back that looks like this, 201 created, instead of 200 okay, right? You submit a different PAN request, 2 different requests, one comes back 201, one comes back 200. Basically, the status code just indicated whether or not the payment server's seen that credit card before or not, right? So as an attacker, we like that. So 201 created, that means, hey, the database server, or the payment server's never seen this before, it's not in the database, it's a brand new token, right, brand new credit card. 200 okay means I've found it, right? So we get the bingo and the Home Alone 2. So anyway, so let's bring on to the next tokenization attack. This is totally different from the side channels. It's replaying tokens. So if you guys remember, so like one of the important things here with tokenization is that we have a token that is a surrogate card for a very specific credit card, right? I can't have a token that's good for your card and my card and somebody else's card. That obviously won't work. And it also has to be good within a specific merchant. You can't go to merchant 1 with my token from merchant 2 and place a transaction. That's kind of the whole idea. Payment gateways are the ones that pioneered this, so that was their idea, right? So like it's a credit card that basically if you get breached, all of the other customers' transactions are safe. That was the whole notion, right? So let's talk about a different trick. So we have an account takeover scenario again, where we've got access to that person's profile, right? We observe the token in the profile, and then we want to actually apply the token to a different customer account within that merchant, right? So this obviously should always fail, but for some reason, sometimes this doesn't, okay? So basically what we're doing there is we're stealing a token inside the same merchant. So inside the tokenized merchant, I'm taking it from customer A and applying it to customer B. There needs to be this notion of, or this property of uniqueness and ownership of that token, okay? That's great. Most people figure this out and get that right, but this next part is a little hazy, right? So second trick, same customer, but a different app context within the same merchant, okay? So take over the account on the web, we take that token from the web and we apply it to, say, a mobile app, or we apply it to another merchant app. So maybe you're a really, really big online retailer and you've got 4, 5, 10, 20, 100 online presence properties, right? And you have one, because again, we like to be efficient, right? So we have one tokenization payment server that supports all of those. So if I steal a token from app 1, can I go over here to app 2 and apply it and just put John Doe's, whatever my victim's name and billing address in there and place a transaction? That's obviously a fail. That's a problem, right? So same thing with if you're brick and mortar transactions and linking mobile apps to retail and converging those spaces. These are actually, obviously this is a hot topic these days, right? So if you can take a token from the online presence and apply it to the mobile app and then go into a store and buy something, you're stealing from that customer, right? That's obviously a big problem. So not only should tokens be unique to a customer, but they need to be unique to a context. So don't reuse a token. Again, it's okay to grow the database. This is a good thing. This is what tokens are for. So tell your DBAs, tell your developers, this is okay. We can have a little bit of bloat because that bloat is our safety net, right? So at the end of the day, we know that obviously solutions. Tokens from merchant1.com shouldn't work on merchant2.com. We know that because obviously payment processors aren't going to reuse the tokens among merchants. But at the same time, tokens from app1.merchant.com should not work on app2.merchant.com, right? So, and this goes back to what I said in the beginning of this talk. So if you are a large-scale retailer and you're doing something like this, you basically are a payment processor. You're a DIY self-hosted payment processor. So a payment processor wouldn't do this for their merchant customers, so you shouldn't do it for your internal web e-commerce property customers, right? So attack number 4, I like to call these careless tokenization bugs. So I've been on engagements before where the browser, which in my case I was a simulated customer, suddenly sent the actual PAN to the commerce server. Okay, that's back to that cooties thing. Why in the world did I just see in Burp or wherever, whatever tool I was using, why did I see that credit card number just go back to the wrong spot? Right? So how can that happen? So let's talk about a couple things. One common thing that we see a lot is JavaScript bugs. Another way is misunderstood widgets in the big pile of code, right? We've got all these libraries, we're wrapping all this stuff together, and we don't understand how all of the pieces work together. So what ends up happening is these logic edge cases kind of tend to emerge, and maybe the edge cases aren't tested in QA because they're kind of weird. And if you're, a good pen tester really likes guessing what these edge cases are and like trying to fuzz and just see them, and so we tend to find them. I'm going to pick on ASP.NET Web Forms because I've written more than my share of that code in that language and platform. If you guys have .aspx pages in your environment. One of the things that ASP.NET Web Forms are notorious for is that they had this, because they were built before the whole Web 2.0 thing, and they tried to make things Ajax-y, and they did these partial page updates to try to make it fresh and not do full page loads on every transaction. Well, one of the really cool properties about that is it sends everything in the form. So you gotta think, why is that bad? Because here, let's look at an example. So I was looking at a particular e-commerce app, and the e-commerce app had a address verification control. So in ASP.NET, you guys are familiar with the term controls if you've ever spent time in there. There's basically a control, a validator that said, hey, is this a legitimate address? Let's go out and check with a post office or whatever to see if this is a legit address on the billing page, while a credit card number was in the text field for the credit cards, right? So what ends up happening is when that validator fires, yeah, the logic on the server side isn't touching that data because it's not looking for it because they just didn't code it. Doesn't mean that it actually isn't going to the server, right? And so in this particular case, card number and the security code number actually went on over there and it's like, oops, right? That's a big bad problem, right? So it goes back to turning this nice little thing into this again, right? So we've got PCI cooties all over again. So if you know any .NET developers that like MVC, they'll love this joke, or maybe we've got some in the room that have seen this T-shirt floating around. So friends don't let friends do postback. In other words, don't use these things that do these weird stuff that you have to really understand all the layers. So that's one example. Another example that we came across was an app that was listening to an on-key press event, okay, in JavaScript. The intent behind this, and I'm still scratching my head to this day, really why they tried to do it this way, but they were basically trying to determine the card type, the credit card type, as you typed, right? You've probably seen, this is a thing that I'm kind of a picky, kind of almost a bigot over now. If I see a transaction page on an e-commerce app and it requires me to hit that little drop down and select Visa, MasterCard, it's like, dude, guys, I'm giving you the card number. You're smart enough to figure that out on the back end. I should never have to do that. But these guys were like, you're right, you shouldn't have to figure that out. So we'll write some JavaScript code that goes and figures it out for you as you type the number. Okay? There's a problem with that. Here's what the transactions look like. So there's a post over to this, let's say it's the credit card type API. Some JSON, here we go, some number. But the problem is, the logic that stopped it wasn't firing for some dumb reason. Like there was do not roll your own tokenization. It's really, really hard, right? So we got 4 411, 411, 411, and it just kept going, and eventually I had it all. It sent the whole thing. On every time I typed in the next number, that credit card number, it just would fire another JSON post over to this API and get back. I don't know what the card type is yet. I don't know what the card. Oh, now I got enough digits. It's a Visa. Hey, it's a Visa. Hey, it's still a Visa. Hey, I got the whole number. Thank you very much. It's a Visa. I am now shopping over here with that Visa. Right? That's the whole, like PCI cooties, right? So, another example. I see this a lot because, we're doing this is a bunch of trickery, right, with JavaScript. So the app server presents that checkout form. It's got the name, the address, and the field in there for the credit card number and all that stuff right there. And it's just got a generic form tab with no action defined on it. Anybody know what happens when you have a form tag with no action? It posts back to the same page. Unless you tell it to do something else, it's going to go back to the app server. Well, the whole idea was this neat little JavaScript library that I pulled in from my tokenization provider, because again, this is the whole notion of separation of duties. I've got the developer building the e-commerce app, and I've got the developer building the payment server. The developers over here building the payment server said, here's this nice little JavaScript library you can bring into your app. Well, for one reason or another, that JavaScript failed to load or execute. It could have been because it was cached. It could have been the server was down. Something weird happened, and it just so happened that while I was testing it, it failed. And then that's really weird. And not only did I failed to check out, right? Because it's going back to the server that's not expecting that to be the next step in the workflow. And it said, oops, error. But that pan went across the wire over there to the comma server instead of the payment server. We got another oops, right? And more PCI cooties. So attack number 5, offensive DevOps. We all love DevOps. So if you haven't figured it out by now, JavaScript. There's lots of JavaScript to do this, to pull this off, right? So tokenization pretty much relies on it. And at some point, if you haven't already had this thought, you need to ask yourself, seriously, we're relying on JavaScript to be our traffic cop, to make sure that we keep our nice little 3 segments together, because we know that there's all these problems, right? So JavaScript's really going to be the thing that keeps us from going sideways, where we've got one big red zone or one big PCI cooties. Well, fun little additional fact about JavaScript that I'm sure everyone in this room knows. JavaScript does not require a build and deploy on the build server in order for the code to be modified out in production, right? We don't have to compile it. So what if you have a DevOps admin that edits the JavaScript files on the web server? Or what if you're in the final stages of a breach, right? And that adversary is on your web front end because, again, that's in that nice blue space where we don't really spend the money and time and everything, and it's tokenized. It's low risk. Right? And that DevOps admin just edits the pages. Do you guys anyone have integrity checking on your JavaScript files on web? Don't even raise your hand because I've never seen it, ever, right? One of the reasons why we don't ever see this is people that have apps like this do continuous integration, which means we push code like 300 times a day, right? So how in the world could we possibly do integrity checking because it changes too often? So let's just say we modify that code, and the JavaScript now sends a copy of that pan to our evil-attacker.com website, right? So, and then for good posterity, we just sent, we did one AJAX request, and then we sent you right back to where you're supposed to go because, we're going to make sure that no one notices and customer still checks out. We just need a copy of that. Thank you very much. Okay, great. So since we have no continuation builds required, what's going to happen? So it's going to get through and it's going to work, right? So what about intentional JavaScript defects? This is similar concept, but what if you have a DevOps admin who decides one day that he no longer is loyal to the company and he decides to intentionally leak credit cards back to his server, right? Not only do you have PCI cooties again, right, because you sent the cards back there, but what logging do you have in place on your web servers? Are you logging full requests? Chances are you're not going to log. It's going to come as a post request and the body's not going to be there, and that's where the credit card is going to be, but yet at the same time it's there. So it leads us to the next attack, right, which is RAM scraping web servers. RAM scraping is not just for point-of-sale systems anymore. With the Target attack, we all knew that Target got hit by RAM scraping POS. It's a tired subject. We all know about that. It's interesting. One of the things that's really interesting is that a lot of people don't understand this. If your web server accepts primary account numbers, or if your web server decrypts encrypted primary account numbers, then that means what? The primary account numbers are in memory, right? And they're in memory in your web server, right? And the thing that people really get hung up on is you probably think it's there for like microseconds. Chances are it's there for minutes or hours, okay? especially if you're using a language like Java or .NET that do garbage collection, or any of these modern 4th generation languages that do all this fancy stuff for managing memory. It's probably sitting in there for a very, very, very long time, especially if you've got, like, say, 100 nodes in your web server farm, and you're doing all this stuff because you're going to divide the load up. Well, that server's got less of a load on, it's got less of a reason to reset the memory and overwrite memory and garbage collect. It's probably there for a really, really long time. So, moral of the story, beware the DevOps admin that says on Black Friday or Cyber Monday, I need to profile this service, right? I need an RFC, I'm going to go start dumping memory and profile this service on this web application, right? So, again, this could be the final stages of a breach. Modifying JavaScript, and then just scraping RAM for the credit cards. Because maybe the application's not doing anything with them, maybe they just go into memory and then it just ignores them, but they're there, and they can be pulled out. So, talked about a lot. To recap, so we defined truncation and tokenization, and we talked about these tokenization attacks. This partial access stuff we talked about, the side channels, the replays, including things like don't reuse tokens in more than one app inside your same company, right? We also talked a little bit about offensive DevOps and RAM scraping. So, we can all relax, right? Because we're tokenized, we're safe. Does anybody have any questions? By the way, we flew through 277 slides in 37 minutes according to my timer. All right? And you're all still awake. So, okay, so the question is, why does tokenization get rid of PCI cuties? And let me pull back the picture. Scrolling. Okay, so this is where everything is in the same scope, right? So that this block of servers in the top right corner of that box, those are all of your web apps, right? And those laptops in the middle, that's your corporate office. Unless you're a big flat network, which everybody was way back. Yeah. Segmentation. It's the notion of segmentation, right? So I'm going to segment off where I have cardholder data, and things that are that touch cardholder data in plain text or have escrowed access to cardholder data. In other words, it's encrypted maybe on the server, but the key is over here. The server that's got the key, those components are all in PCI scope, and everything that touches them is in PCI scope. So everything layer 2, right, and everything that's not firewalled off, and everything that your PCI QSA with his black magic voodoo says is additionally in scope, because that's what they tend to do. All that's the whole idea. So what we're talking about here is we say, hey, you know what? I've got this big expensive thing. So way back a long time ago where I used to work, we have credit card transactions on a mainframe. Mainframes are expensive, they're a pain, they're old, no one wants to really work on them today, right? So we're going to take all of that card data out of there because we don't want to secure this $1 million mainframe environment. We want to secure this $100,000 environment over here instead, right? That's easier. So we can just contain it and then put the tokens over in the mainframe, and then the mainframe, we don't care anymore. PCI goes away. That's the whole idea behind it. Make sense? It's not a requirement, no. It's just a good way to scale it down, right? So you don't have to put your entire organization into scope. Cool. Any other questions? Awesome. All right. Thanks very much, guys.